we are here to see Dr. Richard Weir. He is going to go ahead and do our presentation this fine Tuesday morning.
Okay. Well, good morning, everyone, and thank you for coming to hear what I have to say. It's a pleasure to be here. As you can maybe tell from my accent, I'm not from here originally. I'm from Ireland originally. Let's see if we can get this thing to enter. Step. How do we step? I don't think I can. It's going to be. This is a weird presentation mode. Ah, here we go. Yes, okay. I'm going to rearrange things a little bit here to take advantage.
While he's rearranging, just to let you know, if you'd like to ask any questions during the presentation, if you raise your hand or put them into chat, we'll go ahead and get you called on so that we can answer any questions. Otherwise, we will also have some time at the end of the presentation to answer questions as well.
Yes, okay. Sorry, I had to rejigger things here because the various presentation modes that are all these different screens are not allowing me to step my slides. So I should be ready now. I'm Richard Weir. I'm the director of the Biomechatronics Development Laboratory out on the Anschutz campus, and where we actually design advanced artificial limbs and mechanical limbs for people with limb loss. I also have an appointment at the Veterans Administration because they are one of the primary funders of this type of research. A little bit of history or a bit of who I am and why I'm here is I'm from a little country called Ireland off the west coast of Europe, right there across the Atlantic from the United States. And it's very green there. We get a lot of water, in stark contrast to Colorado. I did my undergraduate in Trinity College in Dublin in engineering, and then I went to Northwestern University in Chicago and did my PhD under Dudley Childress, actually, in the Rehabilitation Institute of Chicago, or what was the Rehabilitation Institute in Chicago. And so this was my lab here. I'm not sure if you can see my mouse or not, but anyway. And then I came out to Colorado in 2011 and and joined the then brand new bioengineering department. Why arms and hands and things like that? Well, I am a sci-fi geek, and so I grew up with the $6 Million Man and Star Wars and Arnold Schwarzenegger with the Terminator. I love all those new Marvel movies and all those things. So I'm basically a sci-fi geek. So, and I have a twin sister who also lost her hand when she was 5. So this obviously plays into it. It's a lot of different things, but as a result of that, we have this laboratory that we have in the basement of the Children's Hospital out here at Anschutz, where we do everything related to the design of artificial hands. And a lot of the issue with hands and advanced hands is that it's not just about the design of the hand, as we might kind of think about here on the sort of lower right corner, we see a bunch of hands, but everywhere else we have all this extra stuff, like how do we control those hands? What algorithm do we use? How do we lift signals off the body to control those hands? Like sensors, like the implantable sensors that we might use. How do we manufacture or fabricate our components? Like we have 3D metal printing. And then there's algorithm development and basic research into how we might, if we ever wanted to use nerves, how would we read or interface with nerves in the body to try and figure out ways to control arms. So this is a lot of what we are involved with. We're involved with sort of all aspects of the problem as it pertains to the design of artificial limbs. Our lab has a 3D metal printer, and we therefore make a lot of things, just 3D print stuff out of steel or titanium or out of plastic to iterate and prototype designs. I believe the design philosophy of fabricate and fail often early is a good, successful way to make things, allows you to iterate things as you are trying to develop something. So let's think a little bit about hands. We are arboreal. We come from trees originally. And so we are these, what they call brachiating animals. To brachiate is to move from branch to branch by hand over hand movement. Okay. This requires us to develop good hand-eye coordination. And probably the evolution of good hand-eye coordination became a self-fulfilling prophecy that caused for the development of brain size to enable the good control of your hands, which then the good control of your hands promoted bigger brain size because you were able to do more with your hands, and becomes this sort of spiral. And so there's current sort of wisdom is, we think of the hand of evolving first. It's subservient to the arm. The hand is subservient to the arm, i.e. the arm's role is to position the hand in space. And so, I don't know, current wisdom says, we were 60 to 70 million years ago, we were brachiating monkeys, or evolved from the same roots as the brachiating monkeys, if you like. And then we have to somehow come from trees, become upright onto 2 feet. The ability to stand upright separates the hands from the feet, and frees the hands from locomotion to basically be able to develop a brain-hand coordination in a better way. Enables you, the freeing up of the hands enables tool use, which enables communication and things like that. We think that the development of the hand and its control, and this is a key concept that I want to think about, is the idea of how do you control stuff? You need the brain, or you need a well-developed brain to be able to control a hand well. Okay, many people say our thumb, and the fact that the thumb opposes our fingers is what separates us from the other great apes. But the bonobo is an example of a great ape that has an opposable thumb, but I would say it's the lack of equivalent brain size to take advantage, or yet of its thumb, that separates us. We have the control to go with the architecture. I want to talk a little bit about architectures. A lot of what we do is making things. And a lot of these systems that we make tend to be highly complex. So we spend a lot of time thinking about, how am I going to make this thing in a meaningful way? And one of the central approaches often in many designs is, do I make a distributed design? Do I make a centralized design? And if you look into the world or look around you, I spend a lot of time sort of considering the world around me and how people have made and solved other design problems before, see that there is this play many times between distributed versus centralized type of approaches. In intelligence, if you like, the human has a centralized control, a brain centralized, going to spinal cord nerves going out, wiring, if you like, going out to your muscles, and sensors coming back from the muscles back up to the spinal cord and into the brain. The brain is your central processor, like your classic microprocessor in a computer, okay? Some of these multiple processor units, they're still sort of centralized in many of their approaches. Other approaches is to have a processor with all its requisite peripherals all in a separate location and have them communicate across distance with each other. And that's more a distributed type of system. And the octopus, I think, is fascinating because it's a biological example of a completely alien intelligence. They're very smart, but they have separate brains controlling each leg, for example. And then they talk between, the legs talk between each other and the eyes. So it's a very interesting, it's a different approach, if you like, to the intelligence problem. The other approach is maybe hive intelligence. Again, this is different architecture again. Many millions of individual things give intelligence on a bigger scale. So it's this an interesting idea of, oh, how do we set up the problem? So the title of the hand of the talk was Dexter Sinestre, right, in the left hand of darkness. And why? Well, our hand permeates pretty much every aspect of our language and the way we talk and communicate. And when we are designing hands, we design for dexterity. And if we are clumsy, we are gauche, or which is left. Everything, if you are, broadly Christian, everything left is the devil and everything right is good. The devil sits on your left shoulder. So you throw salt over your left shoulder to throw salt in the devil's eyes if you spill salt. These sort of traditions come from ideas of right and wrong, left and right, good and bad. And so sinister is left, sinistre. So, and Dexter is right. So the side of light and the side of darkness. So, and for those of you who are left-handed, you have ever so slightly lower mortality than those of, or higher mortality than those of us who are right-handed, i.e., you are likely to die a little bit more quickly than those of us who are right-handed, not because you are left-handed, but because you are left-handed in a pretty much right-hand world. Some numbers for folks, since we're working with people with limb loss, we're working with people with amputation primarily. Pretty much more people have lower limb versus upper limb amputation. About 10 to 1 is about the difference. And it's between 1 to 3 million people with lower limb amputation, about 100,000 people in the US with upper limb amputation. So it's pretty small. Most people think, oh, I want to, hands are cool, right? So we want to build a hand. And therefore, when we're going to help all these people with hand loss. And it turns out, well, actually, the numbers involved are pretty small for who have traumatic loss of arms and leg, okay? The primary cause is farm machinery and industrial accident. right? And then motor accident, and then war. So war is a primary driver of funding in this field, as indicated by the VA, but the primary cause of amputation is farm and industrial accident. Okay. And pretty much 90% of this group, they only have one, they've only lost one limb, which, you know, that's great. And more than, you know, 70% or so are below the elbow. Trans radius is the bone in your arm next to your thumb. So transradial is below elbow. So that says, that's an interesting, this is who we are, this is our target population. When we were talking about the design of artificial hands, we're talking about, you know, 150,000 individuals in the US who have lost one arm below the elbow due to usually farm or industrial accidents. So this means they're usually of working age, and then so usually will want to go back into the workforce. This is just another one of, this is just a chart showing that might be, this is a typical sort of graphic that one would see on an intake form at an amputee clinic, defining the level of amputation. And these are our different definitions of amputation: forequarter shoulder disarticulation, transhumeral elbow, transradial wrist, transcarpal, metacarpal. These are the bones. The carpal bones are the wrist bones. Okay, the radius is there's the radius in the ulna in the forearm. There's the humerus up in the upper arm. So this is our demographic. We've been working, though, on numbers of different prosthetic arm systems for many years. And one of the bigger ones that came out of the Iraq war and the war in Afghanistan was these two arm development projects that we worked on, called the Revolutionizing Prosthetics initiatives. Came out of DARPA, which is our Defense Advanced Projects Agency. And we were the, because we were the red team. There were different teams developing different arm systems. We were the red team because one of our engineers was a fan of Iron Man. So all the original prototypes for this limb system we had in this sort of red anodized aluminum. The resulting arm system you may have seen on different sort of YouTube videos. This is the modular prosthetic limb. The lead institute on this was the John Hopkins Applied Physics Laboratory, and we were a primary subcontractor on that to them, helping them build this. And we worked on all the limb systems in that project. I guess I was called the system architect for this. And so this we put us into a design where we had, this was not a centralized type of design. All the motors had their own intelligence. And then we ran bus systems to communicate up the length of the arm, because then this allowed us to eliminate a lot of the wiring that's is highly problematic if you're running wires across joints. And we had all the motors in the system were custom made. This is a fingertip here that with a motor coil on it, and that went in the knuckle here. Everything on this thing was custom. And it turned out the biggest issue with this wasn't our inability to make the drive. This is a gearbox, by the way. We put the motor in here, we have transmission here. This goes in your knuckle. The biggest issue was the wiring. And you can get a sense of some of this issue. Here's the hand being assembled here. There's a bunch of wires coming out here that we had to run down across each joint and then out across here. Every finger had that, every wrist and joint had that. Running the wires so that they would not break after, a short time was a real challenge.
So this is an arm prototype being demonstrated to show the near natural movement of the hand and arm. Now, a normal upper extremity, including the hand and the fingers, has over 20 different ways, or 27 different ways it can move. This hand, at this point, is built to perform all of them. And as you see, it even can move between the touch the fingers.
Hopefully you can hear this.
In a way that would allow for great dexterity. Here's an example of being able to pick up an object.
So this is the resulting arm out of that DARPA project. It was called the MPL arm, or the Modular Prosthetic Limb. And it was cool, right? We see a fully articulated arm that's able to move just like a human. The big issue, though, is, yeah, the arm is cool, but you can see that there's a chap there behind them who has this full arm on them that they are wearing with a 25 degree of freedom follower. And they flex their fingers, and the hand will follow the position of the user, the command input from here.
Move it, manipulate it. One can see the potential with this kind of
And
movement.
so he's able to control it well, but he has, so for remote control, this is great. The issue is then, how do we then, if somebody has lost, they don't have a full arm to control this, the issue then is, how do you interface the body, so develop interfaces to the body that allows you to pull signals off the body to drive the arm. This arm now went on, was never really used for people with limb loss, but it did go on to help someone. This lady has cerebral palsy and high-level paraplegia, and she's basically paralyzed from the neck down. And so they developed cortical brain control interfaces that sit into her brain. There's a Utah array. This is this array of spikes that then comes off her head and goes off to a bunch of computers out here to figure out her thoughts to try and drive the arm. For someone with a limb loss, this really is maybe not a great solution. You don't want your head cut open to have chips put in there, particularly not if you still have a good arm, right? So here's another arm that came out of this DARPA initiative. It's called from Deca. The Deca, Dean Kamen, who did the first robotics initiative that some of you may have participated in. Well, this is the Deca Arm. It starts life as a prototype system that doesn't look very pretty, but it is functional. And then it becomes a second generation type of system here. You can see this gentleman has a transhumeral level amputation. He has a sound limb. If he was drinking in real life, he would not be using his prosthetic limb to do it. This is a kind of staged moment. He would just pick it up with his sound limb. And so this is a big issue, is, how do we pull signals off the person to drive the arm? Here they're using inertial sensors, and in some cases a foot controller for this arm. That wasn't awfully effective. This arm has since been released to the market. And this is now the Gen 3 version of the arm. It's all electric motors for the actuators, and this will cost you about $100,000 today. And this is research using this Deca hand here. And this gentleman has a nerve interface put into his nerve so that he can sense his fingertips here. So he has fingertip sensors here that sense pressure or force. He has a nerve cuff in his arm that these sensors will cause the stimulation of that nerve. They'll emit current into it through this interface. Okay, but this arm is heavy. So this is like, oh, so what do people really use? And what you're seeing is pretty much anytime you see someone with a fancy arm like this, on the other side, they're wearing this cable operated arm because it's kind of lightweight and intuitive. Okay, here he is with a Deca Arm, full body powered system, and a cable operator. Anyone with a bilateral involvement will usually have a cable operated system on one side and a Myo system on the other side. Okay. So this is what is myoelectricity. Well, your muscles, we can use your muscles. Every time your muscles contract, they make electricity. And we can measure that electricity and use it to create a control signal. And then if we have set them up so that you have a flexor or an extensor, you can do muscle wrist flexion, think of wrist flexion, and you'll generate a signal here, go through an amplifier, drive the motor in one direction. Over here, you'll have an extension muscle maybe, creates a signal, comes across here. This is just an electric field that's created as a byproduct of muscle contraction. Okay, so we have these two main approaches today for control signals, right? We have our well, here. Well, I don't want to get too bad. We have our cable system here, and we have this guy has a Myo system controlling open close. You might have a nerve cuff for feedback, but for the control, the feedback is just giving him sensory information back. But for the control, he's using muscle signals or cable. So here's this is a couple of folks with high-level bilateral involvement. And it's like, this gentleman was a lineman, this gentleman was an electric lineman. They both lost their limbs in electrical accidents. All you can see the common theme here. They're all fit with cable-operated body-powered system on one side, an electric-powered arm on the other side. Okay, and when they're kind of working out in the world, they oftentimes will use their cable-operated system over the powered system. Okay, and you can see this is a Deca Arm powered system. This is actually a prototype one arm with the cable system, Deca Arm here. And then RIC arm. These are all different powered arms, but there's always this cable operated system here. So what does the control look like? So this is this is the same gentleman with both arms, right, involved. And what he's using isn't really even using his cable operated arm that much, right? He's actually using a lot of body English to pull and pull against surfaces and things like that, and rotating things against body parts. So this kind of begs the question, well, this means the control, I mean, to me at least, this control leaves a lot to be desired. It's not awfully pretty. And he's got this sort of array or piano array of chin things that he has to use, or electric switches, and he has to pull against objects. It's not like how you and I might control our hand. And that's just the arm, that's not even the hand. The current hands, there's a whole wave of new hands that are available on the market now, new electric hands that have individual fingers. This is the Biba, not the Biba, Tasca hand. The Tasca has 4 fingers that are able to move, 1 thumb that can move in flexion extension, but also rotate the thumb out and close, so abduction and adduction too. And then this, so that's 6 motors here. This is the Bionic, touch bionic hand. This is an ultra. This is a 6 degree of freedom too. The Bionic is a new hand that's 5 degrees of freedom. And what you can see is, oh yeah, there's these hands that are out there that tend to be controlled though with 2-site Myo, which is essentially open close. So the systems are out there, but they don't have the control that can take advantage of them. And so that's some area that we've been working in a lot. So we aspire to create a hand that could do dexterous manipulation and then to build the interface to do it. Okay, so that's kind of our thing. There's a lot of this, we've worked on all these we've worked on these mechanisms, if you like. This is the revolutionizing arm, the MPL arm, and you could see how, oh yeah, we could manipulate things if we could get the control interface. And so our control interface approach is to use implantable myoelectric sensors, which we would inject and put them into the individual muscles of the residual limb, run them through it's a decode algorithm, it's called signal decode. It's basically, how do I take these muscle signals and map them over into what motors I want to drive in the arm, i.e., how do I know that these muscles are hand open? If the person is doing these 3 signals in some combination, how do I decode that and say, yep, let's put the hand into hand open with thumb abduction or something like that, okay? And then it's like, oh, if I have sensors in here, how do I pull the sensor's information and put it back into the body using some sort of, what approach do I use? And this is where some of our later current work is looking at developing nerve cuffs using optogenetic approaches to talk to the individual fibers in nerves. So the control interface that we use or have developed in the past is something called an implantable myoelectric sensor. If I look at your arm, I chop your arm through in section, you can see like there's all these muscles here in your forearm, right? And so this is your flexor digitorum. This controls finger flexion. There are 2 finger flexor muscles. There is an extensor muscle here, extensor digiti quinti minimi here. These are your extensor muscle. Here is extensor digitorum. This is your finger extensors. If I could put sensors in each of these muscles, because it turns out there's like 33 muscles in your hand and arm relate to the control of your hand. If I could put individual sensors into each of these muscles, I'd be able to pull a signal off of each of those muscles and then map those signals over to their equivalent function in a prosthetic hand. That at least is the idea. That is why if we think you need, or I think you need, implantable sensors. You could, on the surface, which is what everyone had been doing up till now, you put a surface sensor, they pick up the activity of everything below that sensor. So it's not focal. Is the main issue. If I put a sensor on the surface of the skin, it detects all the muscle activity below it. And there tends to be a lot of crosstalk and low pickup, and you can't do it. So the thought was, well, why not develop an implantable sensor that we could maybe inject into the residual muscles in the limb? Okay. This gets us into some architecture decisions. This is a system from a Ripple, they're a group in Utah. They have decided to go with a centralized approach. They have electronics here. This is an implantable system. This is subcutaneous bunch of electronics. And then they run wires from their central location to the target muscles. This has advantages in that you can make the inductive coupling needed to power this. They have a coil on the outside and the electronics on the inside. Is fairly simple and fairly straightforward, short distance. The issue is the wires. The wires flex and can maybe break over time. They can pull out of the target site. And so the issue then is, oh, you can get infections possibly running down the length of the wires. So those are the sort of main issues with this approach. And this is just a close-up showing the main issue here is the inductive coupling. Closer to the skin surface allows you to have good coupling coefficient. So our approach was to develop these little sort of grains of, well, a large grain of rice, I guess, would be what the, we have integrated circuit with radio frequency telemetry in these individual devices that we would then place into the individual muscles, allowing us to get focal recordings in the muscle. And in theory, we could maybe inject them in later. For the first human trials, we used full cut downs. But in theory, you could inject them and therefore use minimal surgery. So this was our concept, which is a distributed approach. And then we have the coil sits in the socket, and the socket, the prosthetic socket, because you're seeing maybe, by the way, we talk about hands, for example. There are hands and components, but they have to bolt to a socket. This would be a prosthetic socket here. You can see there's a bunch of folks with different sockets. So the hands all like this, have common wrist adapters on them, but they have to fit into a socket that looks like this with electrodes and a battery, right? Whereas we replace the electrodes with these implantable sensors. We don't have to worry about that there, but this approach then allows us to put the coil in the socket. These devices are completely passive in the body until the socket is put on and sends power over this coil to the implants. And so, and the muscle then, they're completely embedded in the muscle as well. So that was our idea. This is the first human subject.
I was on deployment in Afghanistan, and on July 15th, 2012, while I was interrogating an ID, it detonated in my face, resulting in the loss of my right arm, and I'm blind in my left eye. With my original Myo, it was very limited in what I could do. With my new setup, with 8 sensors implanted inside, now I have 3 ranges of motion. I can open and close, I can rotate my wrist, and now I can move my thumb independently. And the plus side is I can do everything all at once now. And the other one, I cannot do that. It's just open up a whole nother world.
That's a big deal, by the way, because prior to this, he's got 3 degree of freedom control there. He can control hand open, close. He can control thumb rotation, and he can control wrist rotation. You and I, when we do anything, we do everything in concert. We move our hand and we open our hand and our thumb and rotate our wrist all together in one smooth motion, and we move to it. The current state of the art for control would require him to rotate, open, rotate his thumb. Okay, so to be able to, so this was a great demonstration of the original idea, which is if we could put multiple implants into targeted muscle locations, we could get this idea of simultaneous parallel control. And so, which is what was a big goal for what we were trying to go for with this approach. And this is just kind of showing you the new or the future vision for this system. Is some sort of prosthetic hand. We have a socket. This is all the gear that goes into it. You need there's a telemetry controller, that there's a coil in the socket, and then there's the implants in the arm, right? And so this is our system that we might have. So you can see, oh, and then there's an external system that we have to design and build too, that allows for the clinician, the prosthetist, to set the system up. Okay, so you can see there's a lot that goes into some of these type of systems, but so this is our vision. The IMES has been put into a number of folks here. Walter Reed was this gentleman, the first one, but there's also been a couple of cases in Iceland here, a lower limb case in Iceland, and a couple of cases in Vienna. So this has kind of been kind of exciting. So I think the IMES provide a good means for forward control. Okay. This means we have our IMES, they're in the forelimb, we record them. At the moment, we're doing relatively simple type of control where we map one IMES to one joint in the hand. And so, but if we want to do multiple if we wanted to, we're doing 6 devices at the moment. If we wanted to do like 20 devices, the decode will become a lot more complicated, and we might have to run a more complicated type of algorithm in order to decode multiple devices like that. But the vision is to go to like 12 devices or more, because that's how many different muscles there are involved that you might need to get individual finger control, which is our goal for many of these hands, is to be able to do individual finger control in a parallel fashion. The other side of this is, how do we provide sensory feedback? I mean, we care about sensory feedback because it turns out that without some sort of sensory feedback, you need sensory feedback to do dexterous manipulation. So this is showing you work from Sweden. This woman has a nerve block put on her that's blocking sensory feedback only. So she still has full forward command of her muscles and everything that you might use. So this is like a best case scenario, intact human with full forward command of all her musculature. But we've blocked her feedback, sensory feedback, and asked her to do it. And she can't pick anything up. She can, it's a lot more complicated. And so it's like, oh, if we want dexterous manipulation or the ability to hold stuff and manipulate things, we must provide sensory feedback. So, and that's just for dexterous manipulation. It turns out the need for sensory feedback is a big deal. If we could provide sensory feedback, you could get dexterous manipulation, like I said. But the other thing is you can possibly get embodiment, which means the person will incorporate this foreign device into their own body image. Because a big issue we're seeing with the prosthetic limbs that we fit, they tend to be viewed as the user as being these sort of big, clunky, heavy additions to themselves that they kind of feel are a pain and a hassle to work with. What we are seeing is if we put touch sensors on the fingers and feed those sensor signals directly to the nerve in the individual, they think of the device, they feel a sense of touch with the device, and they feel that that device is now a part of them, and they forgive it for being not great. So this is a big deal. If we can get people to embody their systems, they might use them and accept them more readily. The other issue that we haven't really touched on, which is actually one of the primary drivers for all prosthetic fitting success, is the many folks who lose a limb. Everyone who has a traumatic amputation of a limb retains a phantom sensation of the missing limb. In many cases, that many folks have not just a sensation, but have chronic pain. The idea of putting sensory feedback into the nerve that has been cut, giving it something to do, might help with the elimination of phantom limb pain. So this is a big reason why we're interested in that. Now, we've been working on a bunch of different touch sensors to figure out how we can feed touch signals back into the body. And our goal is to bring these touch sensors back into the nerve of the body. There's work being done by actually Jacob Siegel up in Seaboulder. Just to remind everyone, you can think of here's your brain. This is where motor control and everything is thought. You've got your spinal cord where all your command signals come down. They go out to peripheral nerves. Peripheral nerves look like these bundles of neurons, okay? Thousands of them going to different muscles. You can think of it like being a multi-core wire like this, where each strand is a single axon. And so our vision, if you could tap into here, both for the motor or for the sensory, you would have a way to completely recreate how we control and sense in our bodies. The issue is it's a lot easier to read in the signals, i.e. pump current into this and give someone a sensation, than it is for us to read out, to measure nerve signals. So a lot of work going on in this area. So this is an area where we've been trying to look at. But the idea then is you have a external coil talking to, inductively coupling to a bunch of implants into which the nerve has been instructed to either grow or is cuffed in some sort of way. And then we then have these packages in the arm that decode these signals. So that's kind of the vision for the ultimate nerve interface. But turns out it's a bit of a problem. We believe, yeah, the peripheral nerve interface rather than the brain interface is the way to go, because people with limb loss probably don't want brain surgery and having their head cut open. So if we could access the peripheral nerve, then we know that an arm nerve, a nerve in the arm, we know is an arm nerve. So there's a bit of decoding. So geographically, we know that it's a possibility. The issue, as I've said, is there are thousands of neurons for individual in a peripheral nerve going not necessary, and they're in this wrapped up in this epineurium. Then they're broken further down into these fascicles that are wrapped up in their own perineum. The issue is these fascicles don't necessarily go one fascicle to one muscle. So the decoding, physically decoding them, it can be an issue. The main trade-off that we have ongoing with this is I can stick a cuff on the outside here, on the epineurium, be on the outside looking in, and then I won't be damaging these individual axons. So this is great. The issue is, though, I can't read the individual axons, and so that becomes a problem. So there is this trade-off, this inherent trade-off between invasiveness. I must use a penetrating electrode to get individual neurons or groups of neurons, or I must, or I can be, I can be not selective. So if I want selectivity, i.e. highly focal recordings, I must be invasive. There are no approaches that allow us to get both. Or you can be on the outside where you have cuffs, and then you can pretty much read only at the sort of fascicle level. You have the electrodes on the exterior, and you can read from the different fascicles. And indeed, some of the more promising approaches tend to be these cuff electrodes that go on the outside at the fascicle level. And these have been given in some first in human trials, have been able to give people a sense of touch, a limited sense of touch. And just from that data, we've seen pretty revolutionary type of results. So we've been working in this space for a while, trying to figure out how can we maybe be selective yet not invasive. And so our twist is this idea of optogenetics. The electrical approaches tend to be invasive. You need a penetrating electrode usually that will penetrate into the nerve and then get you individual recordings depending on what it entails. We believe with light, you can be on the outside looking in and then using sort of miniature microscopy type of techniques. You can scan across this and scan down into the Z plane to image these neurons. And these neurons, if they are have been modified to express different types of optical proteins, you can then read out signals from these individual neurons in here. So that's the idea. And we've been working on this idea of using confocal or multiphoton microscopy, building a really tiny one. At the moment, they're a little bit large, and then using optics to focus these onto the neurons in a bundle, in a nerve bundle, okay? And then you have sensory neurons that express one optical protein, and motor neurons that express another. And the type of optical protein, depending on that you express in these neurons, gives you either action potential generation or gives you the ability to see action potentials as they travel down the system, as they travel down the nerve. So that's kind of our idea. So why optogenetics? No electrodes is the big reason. This is the find from the Dustin Tyler's group at Case Western in Cleveland. And this is an external, this is a flat electrode cuff. It's an external cuff, and it's one of the more successful approaches. Okay. So we've been working with, this is some work we're doing with Dr. Emily Gibson and Diego Restrepo and some folks up in Boulder, Julia Gopinoth, Victor Bright, where we're trying to develop a whole optical system that will allow us to interface with nerves. We have this small fiber coupled microscope that's been developed in Emily Gibson's lab. And we have this go through a grin lens that we hold up against a nerve. And we've been working to develop a nerve cuff to hold this grin lens up against a nerve, okay? And then because we can scan across the cut end or across the nerve, we can scan in the Z direction, the depth, the tissue depth into it without penetrating it physically. This is just some work we had done in mice work. This is showing you a sort of cuff that we have developed, 3D print. We 3D printed the mold. This turned out is very the materials were not available to be printed, 3D printed yet, but we're now working to try and do that with sort of nanoscribe to 3D print some cuffs. So our initial work in this area is, okay, this is great. You want to use this optogenetics to show this. Our initial work in this space done by Arjun Fontaine for his PhD was to show, yeah, this is a node of Ranvier here. This is a motor neuron. This is a node of Ranvier. Can we read this out? And if he's stimulating up at the back of the neuron out here, and can we read an action potential out of this? And so the short answer is, if you can see a flash there, we can measure a signal. And so that's kind of what we're showing there, is at that node of Ranvier, we can measure, we were able to read out a signal here, demonstrating at least in concept that yes, we can measure the signal out here, and we can measure graded size out of this as well. So we were demonstrating at least proof of concept of our ability to read out from an individual neuron in a non-invasive type of way using this sort of optical protein approach. So I've talked a lot about a lot of different things about the global sort of system that we wish to try and develop. This gentleman here, we talked about the $6 million man. This gentleman here has an osseointegrated abutment in his arm here. He's got the JHU modular prosthetic limb here. He's got a pattern recognition system. He's had surgery to modify some of his muscles. And he wants to get the nerve cuff from Dustin Tyler. So he's probably getting close to be a $60 million man at this point. So with that, we are funded mainly through the NIH, the VA. We've got lots and lots of partners and players over this time. If there are any questions, I'm happy to take them now. Thank you.
Hey, Doc, I have a question.
Sure.
So if I touch a hot surface, my brain doesn't tell me to stop touching it. It's my nerves, right?
Well, there are two. Yeah, there's two functions at play there usually.
Sure. So do you think we can get to that point of getting those functions into our robotics, our tech?
We could do that now. I mean, it's that's an artificial reflex. You touch something and your initial reaction is to pull away because that's what you're trained to do, right? The other side of that though is you could override that once you realize, oh, I don't want to pull it away. Or you could set yourself to expect to be burned, but still override doing it, right?
Right.
So, you could indeed set up I mean, the sensors are there. You could set up a loop, a reflex arc outside the control of the user that would just pull away in the event of heat detected above a certain threshold or something like that, or rate of rise of heat maybe.
Cool. Thank you.
So you could do that right now, probably.
Okay, so it exists. That technology exists.
Well, the technology is there. So temperature in a prosthetic device is actually not the primary thing that most users want. What they want usually is touch, so that you can measure force and grip strength and things like that. And then touch as in like pressure when you touch someone else.
Right. Okay.
So
one of the questions that keeps coming up through my mind is you keep talking about all the cords and the wires and everything that sometimes they wear out, sometimes those types of things. How far has technology come since you first started on materials that you can use for these things that don't wear out as quickly?
well, I would say the connectors have got a whole lot better over time. Wire is still by and large made with copper, but you have Teflon coated wire for high temperature thing. The issue is it's always the unsexy stuff that breaks in any system that's this complicated. And so it's always and so that means you have to usually resort to things that you have not thought about, like, oh, I need bearings on all my axles that I hadn't really thought I would need. I need strain relief loops on my wires so that when I flex it, and the real test of any of these systems is the fatigue testing, so that we can build it to last 10 minutes, 15 minutes, but can we build it to last 500,000 cycles, or for legs, it's 3 million cycles, So the real challenge, you can get them to work for half an hour or so, but the real challenge, if you're trying to make something for the field, is to be able to get them to last for 3 million cycles. And the fatigue testing is all driven by material properties. And obviously the materials have improved with time, but they're still using many of the same sort of methods. You still have to use redundancy, you still have to use strain relief loops, you still have to use, different approaches that are available, right? If we could beam power, then that would be good, but beaming power gets you into microwave and cooking people, stuff like that.
Don't want that. So, sorry, I'm not sure if it's sorry or Sari.
Yes.
Yeah, it's Sari. My question was, how often do these things need to be repaired? So for example, I was thinking, typically a human's arm, you're born with it, you never really have to repair it unless you do damage to it physically. With these, I'm sure you'd have to service them, like the battery or any power source whatsoever, stuff like that. And then like a follow-up question to that is, how close would we be to auto repairability of those devices, where they are kind of repairing themselves on the inside without any human interaction?
We are not there. I'll show you. I'll just go back to, you need to think of these devices being like your car. It is a mechanical or electromechanical system. These would be state-of-the-art, standard of care hands at the moment. They have a real short mean time to failure. You need to be servicing them usually, just like any car. You might need to have a couple of maintenance runs a year. You need to replace the fingertip sensors. You need to, it's just like a car with an expensive device that needs a maintenance program.
Probably runs more than our car.
Yeah, it's a lot more in your car, actually, because the other issue with some of these, they're very fragile. And so you actually go out and you use your hand like a hammer many times. You pound on stuff with your hand and beat stuff. I mean, I know if I'm doing like some woodwork, I will, push into beat on a chisel with the ball of my palm or things like that to gouge stuff. You do that with these hands, you've got a $30,000 hammer that'll break very quickly. So this is another reason why many of folks use the hooks and the cables. They just tend to be simpler, more rugged. And then when they break, they're just easier to repair. So
Makes sense.
Got it. Thank you.
Thank you, Sadi. Are there any more questions for Dr. Weir? All right. Well, Dr. Weir, thank you so much for joining us on our seminar today. It was very interesting. I know more now about the hands than I ever did before this. So thank you.
Great. Thank you for having me. Thank you, everyone.
Thanks, everyone, for coming.
Thank you, everyone, for listening.
Oh, thank you. Great presentation.
So.